So chapter 4 is titled Exponential and Logarithmic Functions. So we talked about at the beginning of the summer session that we were going to be studying different types of functions, right? And we covered the majority of them, right? We did lines and parabolas and then polynomial functions and rational functions, right? So we have two more, exponential and logarithmic functions. So that's what we're going to study now. So chapter 4, exponential and logarithmic functions. So logarithmic functions, that's the way you spell it, logarithmic functions. So we're going to find out that these two types of functions are very much connected. They're related to each other, right? There's a very special property that connects the two. So before we can get into these two functions, we have to talk about some things about functions that we hadn't discussed yet, all right? That we kind of left for later. And now we're gonna get into those things, and then we'll get into exponential, and we will hopefully get into log functions today also. So 4.1 is titled one-to-one and inverse functions. One-to-one and inverse functions. All right, so let me start with a couple of examples here. As an example, let's take a look at the function f of x equals x squared. We've seen this before, right? That's one of our toolbox functions, isn't it? Looks parabola opens up like that. But I'd like to draw a little picture showing what this function does to a couple of numbers. So we had talked before about like input, output, right? Domain, range type thing. So this is our function f. What would happen if I plug 0 into the function? What would it spit out over here? 0, right? So this 0, I know blue's not going to show up on the camera, and you don't have a blue marker, but that 0 goes to 0, right? Now, what if I plug in 1? Where does 1 go? 1 squared is 1, right? How about 2? 2 squared would go to 4. So this idea of one-to-one means that one input goes to one output, all right? 1 goes to 1. So far, does it look like it's one-to-one? One input, one output. Yes? Okay, what if I plug in -2? Where does -2 go? 4, right? -2 times -2. So this 2 also goes to that 4. So it is no longer one-to-one. I have one input that goes to one output, but we have another input that goes to the same output. Now this is still a function, because to be a function meant one input goes to something, one thing. We can't have two things come out, right? That would violate being a function. But is it okay to have two different things come in and have the same thing come out? That's okay. It's still a function, but it's not a one-to-one function. One-to-one would mean every single line here has to connect separated numbers. Does that make sense? Yes? Okay. So this is not one-to-one at all, right? Not one-to-one. Here's another way to think about it. If I ask you, I tell you, hey, look, I've got a function. It's x squared. And it spit out 4. Can you tell me where it came from? If I say, hey, I'm looking over here, and this got dropped out. It's a 4. Where did it come from? Can you tell me exactly where it came from? You can tell me one of two things, right? But you can't tell me exactly one place, right? This 4 could have come from 2, or it could have come from -2. So that's another way we want to start thinking about things. When we're talking about functions, whether or not they're one-to-one, whether or not they have inverses, we'll always ask ourselves that question. Can I determine where this came from exactly or not? If I cannot, then it's not one-to-one. So let me give you an example of a function that is one-to-one. All right? Let's just take the squared off. All right? Let's take the squared off and draw another picture. And we'll make it a little more interesting. How about we do 2x instead of just x? So if I plug in 0, I get what? 0. If I plug in 1, I get 2. If I plug in 2, I get 4. Now, what if I try some negative numbers? Like, what about negative 2? Negative 4, right? No matter what I plug in, I double it, it comes out something, but I'm never going to have two numbers go to the same place, will I? Right? There's no way I can plug in a number here and it go to the same place that some other number goes to. So this would be one-to-one. So I'm going to put here one-to-one. Check, it is. All right. Now, looking at this picture makes it kind of difficult for us to determine whether or not it's one-to-one, so there's a much easier way to tell if something is one-to-one. Here's how we do it. And I think what I'll do is I'll put our two examples side by side, and I'm going to see if you notice the difference between them. So the first example we had was f of x was x squared. The other example we had was f of x was 2x, right? Let's just draw the pictures. X squared, we said, was a parabola. Goes like that. 2x is a what? The line slope of it is what? 2/1, and it goes through the origin, right? So it should go up 2/1 like that. It should be like this. Okay. So let's see if we can figure out the difference between these two. What did we use to check to see if something was a function? Vertical line test, right? Both of these passed the vertical line test, right? But what about another test where we do horizontal lines instead? So look at this one here. If I draw a horizontal line instead of a vertical line, will I hit the graph in one place only? Yes? So if I go ahead and do that, let me just draw horizontal lines. Notice every line that I draw only hits the graph in one place. Now, why does that matter? Well, think about it. Let's say that this line up here, this was 4, okay? This is 4 units high. Can you tell me where that came from? What? 2, right? 2 would spit out 4. Yes? So by drawing a horizontal line and only hitting once, that means that there's only one place it came from. Yes? What if I come over here and I draw a horizontal line and it goes through 4 up here? There's actually 2 places I hit, right? So where does that one come from? Well, it would have to come from 2 different places, -2 and +2. Do you see the difference between these two graphs? So by simply drawing a horizontal line and looking to see if I hit it more than once or only once, I can tell if it's one-to-one or not. Kind of make sense? Okay, so this thing right here is what we're going to call the horizontal line test. All right? But before I actually write the horizontal line test, I want to write a couple of other things, just some definitions, type language things. Okay, if a function is one-to-one, then we say it has an inverse. So if every input goes to exactly one output, and every output comes from exactly one input, so I draw those lines that go straight across, or if I draw horizontal lines and only hit once, then we say the function has an inverse. All right? Make sense? Okay, so that's just language. Then we have from here what we will call the horizontal line test. Given a function, we use the horizontal line test to see if it is one-to-one. Or I could say, instead of using the horizontal line test to see if it's one-to-one, I could be saying, or it has an inverse. Okay? These mean the same thing. Your horizontal line test will basically give you the conclusion of yes, it's one-to-one, yes, it has an inverse, or no, it's not one-to-one. No, it does not have an inverse. Now, how does the horizontal line test work? Do I need to write it out, or do you understand it just from the picture? Horizontal line test? You understand it from the idea? I mean, because I could write down, the horizontal line test says that if any horizontal line intersects your graph more than one time, then it does not have an inverse, right? Okay, so since vertical line test is something most people get, I'll just assume you can extend that out to the horizontal line instead. Okay, so let's try a couple of, I'm going to give you a couple of pictures. You're going to tell me whether or not these things have inverses or not, all right? So here's your example. Two questions. Function, and then does it have an inverse? Okay? Those are two things. Is what I'm about to draw a function, and then does it have an inverse? How about a nice polynomial function like that? Right? That look like a polynomial function? It is a function, passes the vertical line test, but it fails the horizontal. So this one, I would say yes, and this one, no, right? Horizontal line test. What if I draw this horizontal line? Does that pass the horizontal line test?
Yes.
Yes. It's the one that I draw like over here. That one actually hits it 3 times, doesn't it? Right? Therefore, this function is not one-to-one. This function does not have an inverse. Yes? Okay, what about this one? Same two questions. I'm just going to say F and I question. Here, you like these, right? We just had a test on these. What if you had something that did this? What type of function is that? Rational function. Is it a function? Yeah, it passes the vertical line test. Does it pass the horizontal line test?
Yes.
Yes, it also does, right? Because I start drawing horizontal lines, I'm only hitting the graph once. So that would be yes, yes, right? Do all rational functions have inverses? No. You can think of one, right? You think of one that you drew before that you would have it fail? Well, let me give you an example right here. Function, yes or no? Inverse, yes or no? How about this one? Something like what was on the test. It was there was one that went like this, and it came back like that, and then it went up here. I think it went like this. On this side, it did something like that. I don't know. Is that a function? Yes. Does it have an inverse? No, right? Let me try and record this. If I draw this right here, actually hit it 3 places. So, yes, function, no inverse. Okay, one more. What do you think?
Not a function.
It's not a function. You all agree with that? Vertical line test would fail here. So no, not a function. Inverse. Horizontal line test would pass. Okay, look back in your notes. What did I say when I said I'm going to write a couple of definitions things down here? What did I say? What was the first thing I said? What did I write? A what is said to be one-to-one.
We say it has an inverse or function.
Okay, let me see. Did you write pretty good what I wrote down? Okay, if a function is one-to-one, we say it has an inverse, right? If a what is one-to-one? If a function is one-to-one, we say it has an inverse. So before you can even talk about inverse, you had to have a function to begin with. So once it's not a function, we don't even consider inverse, all right? So this is not even something you could answer. This is not a function. Does it pass the horizontal line test? Yes, but in order to use that, you have to be working with a function. Got it? All right, so that's the visual idea behind a function and whether or not it has an inverse or not, all right? So the first 5 problems in your homework, they give you a picture and then they ask you, you know, is it a function, does it have an inverse, basically. Now, let's take a look at the same 2 examples I started class with when I was trying to get you to see things. The example I gave you was f of x equals x squared. Let's talk about why this is not, why this doesn't have an inverse. We already talked about, okay, because when you say that 4 comes out, you don't know where it came from, right? Right? So here's what I want you to look at. If I draw, we said 0 went to 0, right? We said 1 went to 1. We said 2 went to 4, but then we said -2 also went to 4. Now I'm going to do the arrow separate, right? These went to the same place. That's not good, right? The idea is to try and come up with a way of going backwards, right? Like, how would you, if I gave you 4, how could you get back to 2? By doing what? Taking the square root of it, right? Taking the square root. Or if I could give you 1, how do you get back to 1? You could take the square root of 1, and that's still 1. Square root of 0 would give you 0. So the question is there a way to create a new function that undoes this one? All right? So let me write something down here and see if you follow this. You remember how we started using that notation, f of x, but before that we were using y instead of f of x? Remember that? We said at some point we're going to replace y with f of x. Let's go back to this notation. Can you solve this equation for x? Right now it's solved for y, isn't it? Y is equal to x squared. Can you solve it for x? What would you do? Take the square root on both sides. But when you take the square root on both sides, what do you always have to do when you take the square root on both sides of an equation? You have to do plus or minus, right? And here's the problem. If somebody gives you a y, y is the output, right? This is x is the input, y is the output. If someone gives you a y value like 4, then what's the square root of 4? It's 2, right? So what you're saying is if y is 4, then x has to be 2 different things, right? Positive 2 or negative 2. You see? So what I'm trying to get you to see is that instead of looking at a picture, we can look at it algebraically and see right here when we saw the plus or minus that, wait a minute, hold on. X is going to take on 2 values. If I give it a y value, it's going to have to come from 2 different places. That violates it being able to have an inverse. Make sense? Let's take a look at the other example. So this is going to tell us it's not 1-to-1 because of the plus or minus, right? Let's do the other example. F of x equals 2x. So the picture of this, 0 went to 0, 1 went to 2, 2 went to 4, -2 went to -4, right? Is that what we did? So if I rewrite this, we know this is 1-to-1 already, right? You know it has an inverse. Let's see if we can figure out what it is. So I replace f of x with y. Can you solve that for x? What do? Just divide both sides by 2, right? Or I could say multiply both sides by 1/2. Like that. Now, if I give you a y, are you going to get only 1x? Yes? If I give you 2, you're going to only get one thing, right? If I plug in 2 here for y, what happens? Half of 2 is 1. So if I plug in 2 for y, then x must be 1. And is that where it came from? Did 2 come from 1? Yes. You see? So algebraically, we can look at this right here and we can say, wait a minute, there's no plus or minus. We don't have 2 things coming out of it. Make sense? All of this leads up to how do we determine if a function has an inverse if we can't draw it? Okay, if we don't have the drawing of the function, then can we find a way of getting the inverse, right? Some notation. Given a function f which has an inverse, so let's say we have a function and it does have an inverse. The inverse of f is written f with a little -1 up above it like that. Remember, f was the name of the function. We talked about functions. We said the letter in front was the name of the function. So if you have a function which we're calling f, then if it's a 1-to-1 function, it has an inverse, then the inverse is denoted this way. So f is a function, and f inverse is another function. What f inverse should do is undo f. Okay, whatever f does, the inverse should undo it. So the question becomes, how do we find this, right? If you have a function that has an inverse, how would you find its inverse? Steps to find an inverse algebraic. Algebraically meaning, how do we do it by hand? We already did a couple of problems where I gave you the graph, right? And you could tell me yes or no, it does or doesn't have an inverse. But you weren't able to tell me what the inverse was. Now what we need to do is, if I give you a function, how do you algebraically go and find that inverse function? And here are the steps, okay? The first step is to replace f of x with y. Okay, so I did this already, didn't I? A second ago? We took a function, I said, hey, if you just replace f of x with y, then you get this, right? Now, the next step is a little bit weird. We didn't do this before. Switch x's and y's. I'll explain to you what that means in a second. The next thing you do, solve for x. Solve for y, sorry. Solve for y. in the last step, replace y with f inverse of x. That's the four-step process to finding the inverse of a function. That's what we're going to do. That's what you'll do on your homework for the remaining problems in this section. All right, so let's do this. We'll do the example we just did a second ago, and then we'll go to harder ones. F of x is 2x. Find the inverse. In other words, find f inverse of x, right? Find that. Does it have an inverse? Does it even have one? Yes, because it's a line, right? All lines will have inverses, won't they? Why will all lines have an inverse? Well, except for a vertical line, right? Why won't a vertical line have an inverse? It's not a function, right? Vertical line is not even a function. But any other line, horizontal or any other line with slope, should have an inverse because it will pass the vertical and horizontal line test. So this is going to pass. So let's go through the steps. First step, replace f of x with y. Okay? Second step, switch the x's and y's. Now here's what I mean by that. Everywhere you see an x, replace it with y. Everywhere you see a y, replace it with x. You're not doing any algebra. You're just swapping variables. So this is going to become x equals 2y instead. Why in the hell do we do that step? I'll try and explain it after we do it, all right? Next step, what do we do? Solve for y. So to solve for y, I would divide both sides by 2 or multiply by 1/2. Either way. I like to multiply by 1/2. I know there's not many people who are going to go on and take calculus, but the reason why I would do this instead of x over 2 is because in calculus, you always want to put your coefficients in front of your variables, always. It makes things easier later. So that's just the natural convention. Now what? Replace y with the inverse of f, like that. So I'm going to write it the other way. I'm going to put the inverse function in front like this, and equals 1/2 x. I'm going to box it up. That's my inverse function. Now, I want to draw a picture, okay, to show you what's happening here. Remember we started with this function f, and it took, let's say, it took 1 to where? To 2, right? If I plug 1 into this function up here, f, I get 2 to come out, right? Now, what if I take that 2 and plug that 2 into this function? What happens? Half of 2 would be 1. So it would actually go back to where it came from, wouldn't it? Like this. So what we do is down here we draw an arrow. This should have been an arrow coming this way. An arrow going back this way. This is what the inverse function does. It takes everything back to where it came from, right? So going from left to right, this was x, right? And this was y. But in the other function going backwards, I wanted my y to go back to what? X went to y. In the inverse function, I want my y to go where? Back to x, right? So remember this second step where I switched x and y? The reason I switched x and y is because I wanted my y to go back to x, which means my x goes to y. So you swap the variables. It's a little weird, but that's the way it works. Okay, questions? Those are the steps. That's the boxed answer. While we're doing this, let's take a moment because it's going to come in a little while. Let me draw a somewhat decent graph of those two functions together on one page. So The first line had a slope of 2, right? It looks like this. Okay, that's my first line. Now, so that's f, right? The inverse function was 1/2 x, wasn't it? If I graph this line, it goes through here also, doesn't it? But the slope is 1/2 instead of 2/1, so that means up 1 to the right 2. So I go up 1 to the right 2 would be about here. And if I graph these, if I graph this line, I get a line that looks like this, right? And then there's another line in here. Let me label this one. This is f inverse. There's another line that I want to put in here. It's not part of our answer, but there's something that you're going to hopefully see with this. If I go from the origin, I go out 1, up 1, or out 2, up 2, or out 3, up 3. Don't I get this diagonal line that goes through here? Like this? I'm going to make it dashed. Does anyone remember what that line is? It's a toolbox function. Do you remember what that diagonal, the perfect diagonal that goes through there was called? Well, that's what it's turning out to be here, but in the toolbox, it's called the identity. Remember that one? Okay, this right here is the function f of x equals x. This is called the identity. You can also look at that as being the equation y equals x, right? That means the same thing. So when you look at this, there's so many little subtleties here. I heard axis of symmetry. If you look at this from your point of view, right, and you tilt your head so that this is like up and down for you now, like this, can you see that these two lines are reflections over that identity? If you take this and reflect it over that diagonal, you get this one? That is not a coincidence. That is always going to happen with a function in its inverse if you graph them together. All right? A couple other things that I want to point out. What is this point? What is the ordered pair there? What's the x, what's the y coordinate? 1, 2? What's this point? 2, 1, right? How about this point? If I were to go out 2 here and go up to this function, where would I be on f? If I went out 2, where would I be? I'd be up here at 4, right? So this point right here is 2, 4. What about if I go out 1, 2, 3, 4 here, where would I be on this? I would be at 2, right? 4, 2. What do you notice about these points? Like 1, 2, 2, 1, 2, 4, 4, 2. What do you notice about them? Aren't they just flipped, right? Like 1, 2, if I just flip them over, that point lives on my other graph, right? If I take 2, 4 and flip it, that point lives on the other graph. That's always going to happen with the function in its inverse. All they do is they swap the ordered pairs. The x becomes the y becomes the x. Okay. I don't know, y'all are giving me some weird looks today. All right, so there's function and its inverse. Let's try something more complicated. Same instructions. Let's find the inverse of f of x equals x cubed minus 2. Now let's see how much information you can recall that we've done this summer. Anybody know what that looks like? Was that one of our toolbox functions? X cubed was one of our toolbox functions. What does minus 2 do to our toolbox function? Moves the whole thing down 2. So we should be able to draw this, but let's not worry about that yet. Let's now go through our steps. We're finding the inverse, right? Find the inverse. Okay, so I replace f of x with y, right? Then what? Switch x and y. Now what that means is everywhere I see a y, I put a what? X. Everywhere I see an x, I put a y. Just like that, okay? I've seen people do this instead. So they say, okay, the x cubed, that's going to go there, and then that y is going to go here. That's not what you're doing. You're just, the letter is being replaced, that's all. Okay, now what are we supposed to do? Solve for y. Well, y is right here. It's being cubed. I have a minus 2. So how can I get the y cubed by itself first? Add 2 to both sides. So right now I'm solving. I'm adding 2 to both sides. And then, how do you get y by itself if it's being cubed? Cube root, right? Not square root, cube root. So I take the cube root on both sides. When you take the cube root of something that's being cubed, they kill each other off, right? That's the whole reason. So this becomes cube root of x plus 2 equals y. Now, with cube root, do I have to do plus or minus? No. You only do plus or minus on what? If you do square root or fourth root or sixth root or eighth root, you only do plus or minus when you do even roots. If you do an odd root, you do not do plus or minus. So what if this had been a 4? And I got down here, I would do fourth root on both sides. You would get plus or minus, and then what would you tell me? It doesn't have an inverse, right? Okay. But this one does. Almost done. Fourth step. I'm going to replace y with the inverse, right? And I'm going to put the inverse on the left instead. So here's the original function. Here's its inverse. Any questions on the steps? Let's just check one value to see if this actually works. Let's say I take the number 2 and I send it through the f function like this. What would happen if I plug 2 into f? What does it spit out?
6.
6, right? 2 cubed is 8, take away 2, that's 6. What should happen if I plug 6 into this one? What should happen? It should take back to 2, right? So plug 6 in here. What's 6 plus 2? 8. What's the cube root of 8? 2. So it goes back to 2. Right where it came from, back through the inverse. Make sense? We have found a function that undoes that function. It's kind of like when we were first talking about functions, I compared a function to like a car wash. Remember that? So you send a dirty car in, right? Comes out clean. This is like this really crappy car wash that, you know, you go through the clean car wash, come out clean, then you go through this other special one in the back, and it gets it right back dirty, puts all the dirt right back on your car the way it started, right? That's what this inverse does. Undoes that one. All right, let's if we can, try and draw this, okay? Let's draw a picture of these two, and so I can convince you again that we have that weird reflection happening. All right, so let me start with a graph of this one. We said that it's x cubed. Go back to your toolbox functions. X cubed looks like this, right? And then we're going to move the whole thing down 2, right? So I'm going to move this down 2. Now, what is this point right here? What's that point? 0, -2, right? Which, if I plug 0 in, I'll get -2. Let's try and get a couple of other points. We said, how about if we plug in 1 into that function? What would you get if you plug in 1? Plug 1 into that function. Negative 1. So we have 1, negative 1 is here. Let's plug in another point. How about if we plug in 2? We said at 2 we'd be up at 6. Can you kind of see this part of it happening? Like that? You see that? Now what about, let's get a couple of other points on this side. How about if I plug in negative 1? What happens if I plug negative 1 in here? What's negative 1 cubed? Negative 1, then take away 2, you're negative 3. So negative 1, 2, negative 3 is here. So that's the point, negative 1, negative 3. One more point. Plug in negative 2. What happens if you plug in negative 2? You get negative 2 cubed, which is negative 8. And then you take away 2 more, you're at negative 10. So you're way down here, right? Negative 2, way down here, negative 10. Off the camera, probably. This is negative 2, negative 10. Y'all follow? Okay, now I erased the inverse function, but the inverse function was cube root of x plus 2, wasn't it? That was it? So let's try some points. I'm going to do this in a different color. Let's try to plug in some points into the inverse function instead. Keep in mind, this black one here is f. Its inverse, let's plug 0 in. Whoa, 0's not good, right? You plug 0 in, what do you get? Cube root of 2, anyone know what cube root of 2 is? Not offhand, right? So that's probably not a good one. How about, what's a number I could plug in there that I would know what the answer is? 6, right? If I plug in 6, 6 plus 2 is what? 8, cube root of 8. So you know what? 1, 2, 3, 4, 5, 6. At 6, I get cube root of 8, which is 2. That would be here. Can you think of another point that you'd be able to do cube root of? Can you do cube root of 0? What's cube root of 0? 0. How would you make that 0 in here? Negative 2. So if I plug in negative 2, 1, 2, I should get 0. So I should be here. This one was 6, 2. This one was negative 2, 0. Does anyone see the connection here? Yeah? Do y'all see what I was trying to get you to see on the previous problem? 6, 2 is just what? 2, 6 flipped, right? Negative 2, 0 was just 0, negative 2 flipped. So how could I get some other points without even have to worry about that? Just flip all these. So what's 1, negative 1 flipped? Negative 1, 1. Negative 1, 1 would be here. Right? Let's see, how about this one? Negative 1, negative 3. If I flip that, that would be what? Negative 3, negative 1. So I come down like this. It's negative 3, negative 1. And I think we have one more point, right? This one? Flip it, it would be negative 10, which is way out here. Negative 10, and then what? Down 2, so like here. Now if you draw these, you can probably go back and look in your notes on what cube root of x looked like. It's supposed to look like this. Can you see it there? It goes like this. Goes, this one needs to come up just a little bit. Goes like this. And then like this. Oh shit, I missed that completely. Now, do you see the diagonal? The identity? It's like this. And do you see that it's a mirror image of itself? Okay. On the homework for this section, you're not going to be asked to graph the two together. You're going to be asked to find this algebraically, like we just did. But in the next section, we're going to be working with the graphs more than anything else. So I want to make sure you understand this part now. We okay? All right. Next example, let's find the inverse algebraically of f of x equals 12 over x minus 1. What type of function is that? Rational, good. And we saw earlier, rationals may or may not have inverses. Let's see if this one does. First step, replace f of x with y. Now, swap the x and y values. Okay, now we've got some algebra to do. You all paying attention? Okay, this is important. I need to solve for what right now? I need to solve for y. Y is trapped on the bottom down here, isn't it? So what I'm going to do is I'm going to work to try and get y and release it from the denominator. The way I'm going to do that is using some techniques of solving what are called rational equations. So whenever we have a rational equation, that's an equation that has fractions in it, what we try and do is multiply both sides of the equation by the LCD, by the least common denominator. So I'm going to come in here, I'm going to look at the denominator, y minus 1. I'm going to multiply both sides of the equation by that. So I'm going to do y minus 1 over here. I'm going to do y minus 1 over here, like that. Now I have to have it in parentheses. Why? Especially on the left side. Why do I have to have it in parentheses? You're going to have to distribute the x through, right? What happens on the right side, though? Since this is y minus 1 down here, and this is y minus 1, this is the same as over 1, right? So it's like on the top, and this one's on the bottom, so they cancel. That's why we did it. So what still remains on the right side of this equation? On the right side? 12. On the left side, though, we have that. So what I'm going to do now is distribute the x through. Let's distribute the x. What would we get? xy minus x. What am I trying to solve for? Y. Here's y, right? Let's get this thing by itself. How can I get this by itself right now? Add the x to both sides. If I add x to both sides, what would I get on this side? X plus 12, or 12 plus x, either way, right? And then finally, to get y by itself, divide both sides by x. Now I have y by itself, don't I? That's a little more involved than what we just did before, right? It's not as simple as, oh, just divide both sides by 2. Or, oh, just take the cube root on both sides. We had to actually do a little bit of work for this. So step 4 is to now replace our y with f inverse, right? So step 4, I replace this y with f inverse of x, and that gives us x plus 12 over x. Shall we check to see if it works? Let's just try a number. Here's f. Can I plug 1 into f? No, because I get division by 0, right? So I can't plug in 1. How about 2? Can I plug in 2? If I plug 2 into f, what does it spit out over here? 12 over 1, which is 12, right? And now, according to what I just said, if I take this 12 and I plug it into this one, I should get what? 2. So what's 12 plus 12 here? 24 over 12. 24 divided by 12 is 2. So it does go back to 2 through the inverse. Now, checking that it works for 1 point is not enough to really be sure we got the right answer. Right? Just because it happens once, does that mean it's going to keep happening? No. So it's really difficult to actually check it. You could check it forever because you cannot check every single possibility, right? Yes.
Yeah.
There's a way of doing it, but it's not this way. You can't check each number. All right, let's do another example. That one was slightly harder, would you say? A little more involved? Then you'll love this one. X plus 2 over 1 minus x. Find the inverse. It's a rational function, isn't it? What's the difference between this one and the one that I did before? X is in both the top and the bottom, right? The last one was 12 over something with x. So, first step. Replace f of x with y. Next step. Swap your x's and y's. So that y becomes an x. This becomes y plus 2 over 1 minus y. Yay or nay? Now what? Solve for y? How are you going to solve that for y? You got y's on the top and on the bottom here, right? How are you going to get y by itself? I wish I could do cartwheels. Sometimes I just feel like I just want to do a cartwheel. I've never been able to do a cartwheel. I think if I did a cartwheel or two right now, it might pep y'all up a little bit. Or like a front or back handspring or something like that. Something to kind of wake y'all up. Let's just imagine. Okay, so same thing we did last time, right? Let's multiply both sides by LCD. So let's multiply both sides by 1 minus y. Left and right hand side, in parentheses. What happens on the right? Cancel out. Left side we'll have to distribute. So let's distribute this x through. What would I have on the left side then? X minus xy. Right side, what's still here? Y plus 2. Now, there's a very, very subtle thing happening that's very different than the last problem. In the last problem, if you look back, we had like something over here is like, is xy, was it plus x or minus x or something, right? And we just moved that x to the other side and we were ready to go, right? The problem here is that we also have a y over here. So could you just subtract 2 on both sides and you'd have y by itself? Don't write this down. But do you agree with this? If I subtract 2 from both sides, I would get this. Do I have this equation solved for y?
No.
Not technically, because in order for me to know y, right, in order for me to know the value of y, what am I going to have to know? X and what? And what y is, right? So it's kind of like in order to know y, I still have to know what y is, but that's a circular argument, right? It's like to know something, you have to know what it was. So this doesn't work. We have to get one side of the equation has y, the other side has no y's on it. So here's what I'm going to do. I'm going to take every term that has y in it. This has y, right? This has y. I'm going to put those on one side of the equation. Everything that does not have a y, this and this, I'm going to put on the other side of the equation. So I'm going to separate them, left side, right side. It doesn't matter which side you go. So what do you say I take this 2 to the other side? How would I do that? Subtract it. Then how about I take the negative xy and put it to the other side? How would I do that? Add it. So I'm going to add xy here, which will cancel. Add xy here, which will just join the y. And then I'll subtract 2 on both sides. So here's what I'll have. I still have this x on the left side. I subtracted 2 on both sides, which meant I have minus 2 here. Then I had the y on the right side. I didn't touch that one. And I brought this one over by adding xy on both sides. So it becomes plus xy. Agreed? Now, do you agree that both terms on the right have a y? If both of these have a y, can I factor a y out? Can I do this? Can I do that? Let's pull a y out of each of these, and you'll be left with the 1 there and just the x here. Now what? I can almost see the y. It's looking at me there. How can I get that y by itself right now? Get rid of the 1 plus x. But it's being multiplied, right? So I have to come through and divide both sides by 1 plus x. So at this point, I'm going to divide this side by 1 plus x. Whatever I do that side, I must do this side. These will cancel, and what am I left with? Y equals x minus 2. X minus 2 over 1 plus x. Now I have it solved for y, don't I? So my fourth step is my final answer. The inverse function is x minus 2 over 1 plus x. Now if you're looking at this problem going, hey look, it's just this, right? But the signs are different, right, aren't they? That's what I'll do in a test. I'll just switch the signs. Well, unfortunately, it doesn't always work out that way. It's just a coincidence here that it works. It won't work in general, so you do need to go through the steps. So I'm looking on the next test, guaranteed you're going to get a problem like this. I'm looking to make sure you know how to do all the algebra involved with this. All right? Now, shall we verify real quick? Sure, I'll verify. If I were to take, let's say, 2 and plug it into F, what would happen? 2 into this. 4 over 1 minus 2 is negative 1, so 4 over negative 1 would be negative 4. Now, if I plug negative 4 into this, I better get 2. What's negative 4 minus 2? Negative 6. What's 1? So we have negative 6 on top. What's 1 plus negative 4? Negative 3. What's negative 6 over negative 3? 2. So it went back. Okay? I don't need to see that, but that's a way you can check your work. Just, I mean, if you're skeptical, just try one point. If it works, then you can probably feel pretty good that it's hard to accidentally get the inverse. You know what I'm saying? So this is a way of checking. All right, well, let me give you your homework from this section. For page, this will be page 420. 7 through 15 odd. 41 through 47 odd. '63 through 73 odd. For these, just find the inverse, okay? The instructions can be a little confusing, right? Like on number 41 through 47, the instructions say, for each function, A, find any 3 ordered pair solutions. Then algebraically compute the inverse, and then verify and all this stuff. I just want you to do what we just did in class, okay? Just what we did in class, the 4-step process for both this and this group. This group were the ones where you look at the picture and you just say, okay, yes, it's a function, it doesn't have an inverse. Understand? All right, now, let's move on. Do we want to take a quick break? Let's do a quick break. Y'all go just run up and down the hall like 5 or 6 times. Get your heart rate going or something.
don't even have this turned in, you're just gonna, because it's all.
Oh, no, that's great. No,
It's
keep
in the
going.
middle of everything.
That's great.
Okay.
Sure. I'll pass it. I know you're gonna go right. Give me just a second. We only have, what, 2 more weeks? Let's see. So you won't be here the 24th?
Yeah.
Okay, so what, yeah, we're probably gonna have to move it to the 29th. It's hard to say. Let's see how today and Thursday go. I would hate to do it Tuesday, because it'll be like a week from today.
Yeah.
But if you can't make Thursday, we can work something out. I mean, that
Yeah, I
would be,
just wanted to give you a heads
yeah,
up.
that would be the most likely day that I would do it. but we would do a makeup or something. Yeah, you wouldn't have to worry about that. Okay.
Test.
You can. If I can. What's your name?
Sneaks.
Okay. There you go. All right, I think that's been about 5 minutes. Yes? Close enough? Okay, we are going to start exponential functions. Oh, the sign-in sheet, let me get that passed out. We need that rain, come on. Reminds me. Sign-in sheet, I'm going to start it back there. All right, here we go. You don't need to write all this down because I've already talked about this before. We've studied so far these 4 types of functions. Lines, that's something like, you get, line is a good example of someone who gets paid a certain amount per hour. Maybe they get a base pay. And so, the number of hours they work, their money basically goes up linearly. Parabolas, quadratic functions, we're good at modeling like things being thrown through the air. Polynomials, things like stock market trends, things that go up and down, oscillate back and forth, right? We saw that with polynomials, up, down. And then the rational functions, we were talking about like the probability of someone living to a certain age, or probability a light bulb will still work, something like that, right? So that's what those, for just some examples of how you could use those 4 types of functions in the real world. Now, let's look at this new type of function called an exponential function, which is extremely important in the real world, used all the time. And I'm going to try and motivate the exponential function by giving you a few examples. So, first example is going to be the folding paper example. So I'm going to make a good old t-table. Remember when we used to do t-tables like x and y? But instead of x and y, I'm going to put here a number of folds, which we will call our x. And then over here, the number of rectangles. All right, and that'll be our y. Okay, so I have a piece of paper here, right? How many folds have I made in the paper? None. So I have 0 folds. How many rectangles do you see? 1, right? 1 rectangle. Okay, if I fold this 1 time, you just kind of draw along that edge. When I open this up, how many rectangles will you see? Should see 2, right? My 2 rectangles. So if I fold it 1 time, I get 2. So if I now go and I take it and I fold it that 1 time, but now fold that again, I get 4 rectangles. So 2 folds gives me 4. How many rectangles will I get if I fold it 3 times? What do you think? The most common answers I hear are 6 and 8, right? So there's a pattern here. It looks like it 2 and then 4 and then maybe 6, right?
7.
7, 7.5. So how many do we have? 4 down here, 4 down here. We have 8. 3 folds gives me 8. How about if I now fold it a 4th time?
16.
Make it 16? So 4 across the top, 4 down the sides, and so we get 16. Do you see a pattern? What's the pattern? The number of rectangles is doubling each time, right? You started with 1, and then it doubled to 2. Then that doubled to 4. You double 4, you get 8. You double 8, you get 16. So if I fold it one more time, how many should I get? 32, right? Trust me, it's 32, right? So 8 across the top, 4 down the side, 32. Now, if I could go again 6 times, right? Has anyone ever seen that Mythbusters where they try and do this?
Yeah, they use a hanger for the.
Yeah, they use like an airport hanger and they get this huge sheet of paper and they get it and they roll over it with a steamroller and they try to get the folds all nice and tight. Okay, so if I do this again 6 folds, I should get how many? 1, 2, 3, 4, 5, 6, 7, 8, and then down the side, let me see, 1, 2, 3, 4, 5, 6, 7, 8, 64. So if I could go further, see, 6 gives me 64. Now, in Mythbusters, which is a show on used to be on Discovery Channel, they try and bust these myths. There's a myth that there's a certain number of folds, like a maximum number of folds that you can actually get in a piece of paper. I don't remember what it is. I think it's like 13 or something like that. But because physically, like they had a sheet of paper filled up in an airport hangar, and they like folded it over once and then twice and rolled over with the steamroller, and they could only get, I think, maybe, I don't remember. Can't remember. It was in the teens, okay? They definitely didn't get past 20. All right? So let's see why maybe they couldn't get past, let's say, 15. So we would keep going down here, right? What would 15 give us? Now this is the motivation of why we're doing this. I think if I asked you how many you would get with 7, everyone would just do what? Just double that, right? And then if I said do 8, everyone would just double that. So to get to 15, don't you have to complete filling out this table until you get to 15? Yes? That's one way to do it. But what if I said, okay, do it if you could, what about 40 folds? You would have to complete the table all the way to 40, right? What if instead we had a function that was able to take us straight to the answer? Like when we plug in 0, it should spit out 1, right? When we plug in 1, it should spit out 2. When we plug in 2, it should spit out 4, so on and so forth, right? What we're trying to do is find a function that does that for us. Well, it's not like any function we've seen up to this point. It's not a linear function. It's not a line. It's not a parabola. Okay? So it's not like x squared or something like that. It's not a polynomial, so it's not like x cubed, x to the 4th, x to the 5th. Okay? It's not a rational function. It is an exponential function. So let me try and help you see it. Do you agree that 2 is 2 to the 1st power? Do you agree that 4 is 2 squared? Do you agree that 8 is 2 cubed? Do you agree that 16 is 2 to the 4th? Do you agree that 32 is 2 to the 5th? Do you agree that 64 is 2 to the 6th? Right? What is 1? 2 to the 0, isn't it? I mean, it is, right? Anything to the 0 is 1. Do you see that all of these things coming out are always 2 raised to something, right? And what is the thing, what is the power up here? That's what we're plugging in, right? The 3 up here is coming from here. The 4 here is coming from here. The 5 here is coming from here, right? So what stays the same in our function the whole time? What stays the same? The 2. What changes? That thing up there, what do we call that thing up there? The exponent. The exponent is the thing that changes. The exponent is the variable. Therefore, we call it an exponential function. So let me write down what this exponential function would look like. It would look like this. F of x should equal 2 raised to the x. The 2 always stays the same. The exponent is the thing that changes. If I want to know what 2 to the 0 is, I plug 0 in here, I get 1. If I want to know what 2 to the 1 is, right, I plug in 1, 2 to the 1 is 2, so on and so forth. Yes? Now this is where you have to have your calculator if you're going to want to do something like this. So if you have your calculator, and I would say from this class forward, you need to have your calculator, right? Not your phone. I brought my phone today because you need to know how to use your calculator for the test. You don't want to be, especially on this next test, you don't want to be the first time you use your calculators the day you walk in to take the test, all right? Because you got to know how all your keys work to do these, because every calculator is different. So I'm here to help you learn how to use your calculator to do these things, but if you don't learn it by the time of the test, which we're thinking is probably next, was it next Thursday? Yeah, that's what we were saying. It's scheduled for next Tuesday, but we're going to push it to next Thursday. That'll be our last test. That's tentative. I might even push it to the following Tuesday. It just depends. The problem is I don't want to have the test the day before the final. Because we only have next week, and then the following week we have Tuesday, and then that Thursday is our final. Okay, so on your calculators, everyone, let's see if you can find a way to do 2 to the 15th power. And then we'll talk about why you can't fold the paper that way. What is it? See how you do. 32,768. 32,768. Does anyone have their calculator with them right now and is trying this but can't get it? Because I can come around real quick and help you. If you know how to do it and your neighbor's sitting there going, oh, no, maybe you can help them. Everyone got it? Why does it seem not possible to be able to fold the paper 15 times on itself? Think about that. If I start with this sheet of paper, right? Right? If I fold it once, how thick is it? 2 pages, right? If I fold it twice, how many pages thick is it? 4 pages thick, right? If I fold it 3 times, how many pages thick is it? 8. If I fold it 4 times, it's 16 pages thick. 5 times, it's 32 pages thick. If I can fold it 15 times, how thick is it? 32,768 pages, right? This book is only, and this is thinner paper, but this book is roughly 800 pages. So less than 1,000. Imagine 32 books stacked up. That's how thick the paper would be. So does it seem like that would be really hard to do, right? So there becomes this physical barrier where you can't do it. Now theoretically we can, right? If we could do it 15 times, what would we get? How about 2 to the 40? Let's see what your calculator says to that. Overflow, or do you get O-flow on yours? Does it say that? Oh, so it did give you a numerical answer. Okay, can I borrow yours real quick? Okay, so this particular calculator is saying 1.0995 and then a bunch of other numbers. At the very end says E12. All right, that little E12 means that you're going to take 1.09. Your answer is not 1.09. It's 1.0995. Move the decimal point 12 places to the right. So I'm going to take 1.095995, and you had more numbers, but who cares? I moved it 12 places to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These all become zeros. That's my new decimal. Okay, this decimal is gone. Comma, 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 comma. All right, what is this? This is thousands, right? This is millions, billions, trillions. So if you could fold the paper 40 times on itself, you would have roughly 1 trillion rectangles. And that's just plugging in 40, right? That got big really fast, didn't it? I want you to compare that to this. What we just did right now was 2 to the 40. I want you to compare that to 40 to the 2. 40 squared. What I'm trying to get you to see is the comparison between this function and the function we studied before, which was this backwards, right? X squared is a parabola. 2 to the x is an exponential function. If I plug in 40 here, I square the 40. If I plug in 40 here, I take 2 to the 40th power. We already know 2 to the 40th is 1 trillion. What's 40 squared? 1,600? It's nothing, right? So x squared looks like this, right? X squared was this parabola. We know that x squared got bigger as we went out, right? But this exponential function is insanely big. Like it's taking off and it is just going really quick, right? Really fast it's growing. Which is why you'll hear people in the real world, or you're watching the news or something like that, people love to throw the word exponential around. Oh, it's growing exponential. The crime rate is growing. Obesity is exponential. They just love that word, right? Because most people interpret exponential growth as being fast, right? That's an example of showing you why it is. Now, while we're on this topic of using this function, f of x is 2 to the x, I want us to look at that table again that we had. It was x and y, it was 0, it was 1, it was 1, it was 2, then it was 4, then it was 8, then it was 16, then it was 32, then it was 64, then it was 128, then it was what? 256. Anybody recognize those numbers? Anybody recognize these numbers on the right side here?
That's where you ran.
Yeah, you always see that with computers, don't you? Like, how many of you have an I something? Okay, iPhone. How much storage do you have on the iPhone? 16 something, right? 16 gig, or you get the 8 gig, right? They never offer a 13 gig iPhone, do they? Okay, there's a reason why they always go in the increments of powers of 2. Anybody know what? Anybody know how a computer works? What's the only thing a computer knows? It's pretty amazing when you go back to like really what, these computers. Your phone is a computer. Every computer, it only knows 2 things, right? Every computer knows 2 things. On, off. There either is a signal or there is not a signal, right? When you have your memory, right, is a picture. You have a picture you took, right, as a selfie, whatever it is, right? That's stored somewhere. I've never done a selfie, so is that right? Hold it. Yeah, you hold it, whatever. Doesn't matter. So when that's stored on your phone, right, it's a file. And that file is basically a bunch of yes and no's. So whenever you open it and it's trying to figure out what on your screen to do with that pixel, what color it's going to be, the yes and no's, the zeros and ones, tell it what color it's going to be. But all the computer knows is on and off. So on, in a computer, on is represented with 1, and then off is 0. Only 2 possibilities, so everything has to be in powers of 2. Everything. So you can have, one group would have 2 things in it, If you have two groups, you would have 4, then 8, then 16. So everything is what we call binary, one of two possibilities. So when they're making RAM or storage on a phone, it's always going to come out in one of those powers of 2. Little side note there. What else? How about anybody watch NCAA basketball, men's basketball? Every year there's this big thing, right? What do they call it? The March Madness, right? You all heard about that, right? March Madness. How does it work? How does March Madness work? You have a tournament, right? How many teams join the tournament? It's different this year, but whatever. It's usually about 64, right? You have 64 teams join the tournament. So what happens is in round 1, you have 64 teams. So you have let's say team 1 and team 2, they play each other, right? And then the winner goes on to the next round, right? Round 2. Let's say round 2. Then team 3 and team 4 play each other, right? Whoever wins that goes on and they play the winner of that one, right? With me? So, at the beginning of the tournament, all these different websites allow you to fill out a bracket, right? They tell you, here are the 64 teams. You go in there and you fill out the bracket. You go ahead and determine who you think is going to win. Before they start playing, you tell me who's going to win this game, who's going to win that game, then who would win that game, who would win that. You fill out the whole bracket. You get to the very end, you say, who's going to be the champion, right? They say, if you can fill out your bracket correctly, right, then they'll give you whatever, right? Even, who was it, Buffett, Warren Buffett offered $1 billion, was it $1 billion this year? For anyone who could fill out the bracket correctly. $1 billion, if you could do it, right? Well, let's just look at the math behind this just a little bit. Okay, this first game, right, has only 2 possibilities for a winner, right? 2. So I could pick one of 2 ways here. This game has how many possibilities? 2. And the next game has how many possibilities? 2. How many games will take place in the first round? 32 games, right? So that means I could pick the first game 2 ways, second game 2 ways, right? So that's 32, that's 2 times 2 times 2, 32 times. That's 2 to the 32. That's how many ways I can pick just the first round. Now we get to the second round. How many games will be played in the second round? 16 now. Each of those games has 2 possibilities. So there's now 2 to the 16 ways to pick the next round. Now the next round is how many games?
2 to the 4.
Half, right? So 2 to the 8th, right? Now the next round would be 2 to the 4th, and then the next round 2 to 2, and then the next one 2 to the 1. There's 1 game left, right? Now remember properties of exponents. If you have the same base and you multiply, what do you do to the exponents? Add them up. So let's add this. 32 plus 16, 48 plus 8, plus this, 3. 2 to the 63. Somebody on their calculator, 2 to the 63?
Oh, that's a lot.
Now I'll write that down. 9, 2, 2, 3, 3, 7, 2, 0, 3, 6, 8, 5, 4, 7, 7, 5, 8, 0, 8. And I may have missed the number in there. There you go. All right. Millions, billions, trillions, gazillions, gabillions. I don't know, right? It's like one of those, what's Austin Powers. What's Austin Powers? What's that? Is that a movie with Austin Powers where he's like, I want a gazillion dollars or something for them. $1 bajillion. So this is like 9 bajillion, right? I mean, that number, how many people are on the planet? I mean, like, just roughly, how many people are on the planet? Billion? A couple of billion? Whatever. So here, this was million, so here we go. Here's 6 billion. I say that's about how many people we have. Okay? So if we just take this and divide it by 6 billion, you'd be left with, you would basically kill off these numbers if you divide it by 6 billion, right there. Now, what is this? This is millions, billions, so you'd have 9 billion. So what you would need is if every person on the planet each filled out 9 billion of these, each person filled out 9 billion of these, all different, okay? Everyone does it different. You do your 9 billion, you do your 9 billion, you do yours, everyone does it, but no one has the same one, right? Everyone on the planet does that. We're guaranteed a winner. See what I'm saying? The number is so astronomically large that someone like Warren Buffett is willing to say, you can do that, $1 billion, because the probability of it happening is less than, you know, hitting the lottery 100 times in a row. I mean, you know what I'm saying? It's just, but remember, is it possible? Can someone fill out a bracket correctly? Yes, absolutely. I think the record is someone got through the first round, correct? And I think got, of the 16 games here, got like
I think this year they got both the first and second round.
first and second round? Okay. So may have gotten to the third, but no one, I mean, there's 1, 2, 3, 4, 5, 6 rounds. You know, getting through the first one is a big deal. And you have to remember, it's not a coin flip, right? If Duke's playing UTSA, odds are, at least nowadays, right now, it's probably going to be Duke. You can kind of, you know, go with that one. But if you're just blindly filling out brackets, okay, I think I've talked enough. I like to try and talk a little bit about exponential functions, and because they do come up a lot in the real world, so you know, get us somewhat interested in them. All right, so here's the general idea. An exponential function of base A is, well, I'm just going to say an exponential function of base A. So what is an exponential function of base A? It's any function where your x is up here in the exponent, and there is a number down here. This A is a number. So A is a number. A must be greater than 0. A cannot be equal to 1. That's what it takes to be an exponential function. You have to be a function where you're a number raised to x, the number has to be positive, and the number can't be 1. Why can't it be 1? What's 1 raised to any power? Itself. So that would just be like a constant 1 function, which would be boring and it's not doing anything. So we throw that out. We also don't have a way of defining what a negative number to a power would be. So we throw out the negatives. Okay? That's what an exponential function of base A looks like. Here are some examples. F of x equals 2 to the x. That's the one that I just did, right? Here's another example of an exponential function. 1/2 to the x. Is that an exponential function? Does it qualify? What's the base of that exponential function? 1/2, right? Is 1/2 bigger than 0? Yes. Is it 1? No. So we're okay, right? So this is the base 2 exponential function. This is the base 1/2 exponential function. All right? Would this work? Is that an exponential function? What's the base of that exponential? Square root 2. Is square root 2 a number? Is it a positive number? Yes. Is it 1? Square root 2 is not 1, right? So that works. How about this? F of x equals pi to the x. Is pi a number? Yes. We usually use the symbol pi for it, but it's like what, like 3.14 something or another, right? So it is a positive number, it's not 1, so that, I mean, I could use pi as my base if I wanted to. And I could keep going forever, right? There's all sorts of exponential functions out there. So the next, I guess, kind of question would be, what do these look like, right? I mean, when you graph them, what do exponential functions look like? So let's take a look at a graph. Let's do a sketch of the one with the folding of the paper. 2 to the x. Now we had made a table, hadn't we? We had started this table. We had plugged in 0 and it had spit out 1. We had plugged in 1, it had spit out 2. We had plugged in 2, it had spit out 4. We had plugged in 3, it spit out 8, right? And then we kept going, but that's good enough for now. Let's just plot those and see what we get. And when you draw this, I want you to kind of follow what I'm doing here. Give yourself some room in both directions like this. The first point here, 0, 1, right? That means I just go up 1, and I put a dot. The next one, right 1, up 2. Next one, right 2, up 4. And then the next one is the one that starts to take off, right? 3 goes to where? 8. So I'm going to go off my page here. And I'm not going to do 4 because we're at 16. That'll be up there. So far, doesn't my graph look like this? Somewhat like a parabola, right? Somewhat. But we said it's growing even faster than the parabola. Remember? Like we went out to 40 on the parabola and we're at 1600, but we go out to 40 on this, we're at 1 trillion. What we have not looked at is whether or not we can put a negative number in here. Now I said the base can't be negative, right? But can I plug a negative up here? So let's try it. If I plug in -1, I get 2 to the -1, don't I? What does 2 to the -1 mean? So do you remember this property of exponents? X to the negative n equals 1 over x to the positive n. Property of exponents. If you have a negative power, you can drop it down. Remember that? So doesn't this really mean 1 over 2 to the first power? Which is really just 1/2, isn't it? So if I go to the left 1, I should go up 1/2, and I should be here. Can I plug in -2? If I plug in -2, that's 2 to the -2. That's same as 1 over 2 squared. So using the property again of dropping it down, making it a positive exponent. What's 1 over 2 squared? 1/4. So that means if I draw it, if I go to left 2, I go up 1/4. What's happening? It's getting smaller, right? What if I go to -3? What am I going to get? 1/8. What if I go to -4? 1/16. -5. 1/32. -6. 1/64. -40. 1/1 trillion, right? 1 over 1 trillion, which is still a number, right? It's very small, but it's 1 divided by 1 trillion. So what we're having here is this is getting closer and closer to the x-axis, isn't it? What do we call that when we get close to something like that? What do we call it with rational functions, that thing that we went towards? The horizontal asymptote. Right, so what we have is off the left side of this graph, I have a horizontal asymptote coming this way. I'm going to put HA right here. See it? So to the right, this thing is blown up, right? Taken off to infinity, going way up there. To the left, it's getting smaller and smaller and smaller, getting closer and closer to 0. What's the domain of this? Domain. Shit. Remember how we did this? If we look at the graph? Does my graph exist over here? Always, right? My graph exists over here? Always, right? So my domain is negative infinity to infinity. How about range? Do I have anything as I move from the bottom up? Do I have any graph yet? No, not until when? Right here, right? Right about there. And then from there up, I've got graph. From 0 to infinity. Now, do I include 0? Do I ever hit the x-axis? No. So I'm going to say 0 to infinity. Notice the parenthesis on 0. This is a good example of what we call exponential growth. As you move from left to right, you are growing exponentially. Now, let's do a similar problem. I want to change the base. Instead of using 2, I want to use 1/2. And I want you to see the difference in the graph. By the way, this is how we will graph these, all right? We're just do a quick t-table, we'll draw it. So it's not like, okay, there's this 5-step process. It's just make a quick t-table, draw your picture. Okay, so for this one, we need to plug in some points, don't we? So the points I'd like for you to plug in when you're doing this like on a test, let's just all do the same points. We'll do 0, 1, 2, 3, and we'll do -1, -2, -3. We'll just always use those, what, 7 points? Let's always use those 7 points to graph our exponential functions. If I plug in 0, what do I get? What's 1/2 to the 0? 1. What's 1/2 to the first power? 1/2. What's 1/2 to the second power? It's 1/2 times 1/2, right? Which is 1/4. What's 1/2 to the third power? 1/2 times 1/2 times 1/2? 1/8. Just multiplying straight across, right? 1's across, 2's across. All right. Now, what's 1/2 to the -1? Well, another property. If you have a fraction raised to the -1, you can flip the fraction over to the +1. Another property of exponents. So fraction to the -1, flip it, +1. So if I take 1/2 and flip it, it becomes what? 2. Okay? If I take 1/2 to the -2, what do you think happens? Flip it and square it instead. So this becomes 2 squared, which is 4. And then what about the last one? 8. Does this look familiar? Doesn't it look like what we just did, but kind of backwards? If I plug in 0, I get 1, right? But if I plug in 1, what did I get? 1/2. Plug in 2, I got 1/4. 3, I got 1/8. And then what does it look like is happening? Getting closer and closer and closer to this horizontal asymptote, right? As I go the other direction, though, At -1, where was I? 2. At -2, I'm at 4. And then at -3, I'm at 8. So it goes like this. Very similar to the other one, right? Isn't it just kind of like flipped over? What do you think was the reason why it was different? That it went down instead of up like the last one? What do you think? What do you think determines which way it's going to go? What? The base, all right? The previous base was what, 2? This one was a half. Somehow that base dictates which way it goes. So I'm going to summarize that in my next note. This was just 2 examples. Your first 2 problems for homework are you're going to graph in your homework 3 to the x, and then the other one's going to be 1/3. So you're going to go through 2 tables, you're going to draw your pictures, all right? So some of the graphs, let's say graph properties. Okay, so here's the deal with exponential functions. You're going to have, with all exponential functions, one of 2 possibilities. You're going to have one of them that it goes through 0, 1. Now that should always happen, right? Because if I plug in 0 for x, anything to the 0 should be 1. So that point should always be there. It could go down towards a horizontal asymptote like this, and then grow exponentially up like that. Or it could be flipped over where it still goes through this point, but goes this way, down, and this way up. Okay? It'll do that on the left if a is greater than 1. Right? 2 to the x did this. 2 to the x did that. 3 to the x will also do that. Which one do you think grows faster, though? 2 to the x or 3 to the x? Which one do you think will get bigger faster? 3 to the x. Think about it. What's 2 to the 40? We said a trillion. 3 to the 40 on your calculator would be even bigger. So the bigger the base, bigger than 1, the faster it's going to take off. And then this one will happen if what? If it's less than 1. But remember, a had to be bigger than 0, right? So like a fraction, 1/2, right? 1/2 was between 0 and 1, so it went this way. If we use 1/4, it'll go this way also. Go with me? On both of these, we have horizontal asymptotes, right? Y-axis? No, that's not the y-axis, that's the x-axis. Over here, same thing. Horizontal asymptote, x-axis. What's the difference, though? Opposite sides. So if I asked you on this graph, what's the left-hand behavior, you would say it gets closer to 0, wouldn't you? What's the right-hand behavior of this one? Goes up forever, right? This one, the left-hand behavior goes up forever. Right-hand behavior goes towards 0. With me? Okay. Now, I didn't do domain and range on those, but for both of those, domain, we'd already talked about. Domain on both is what? -infinity to infinity. Range was 0 to infinity, not including 0, for both of those graphs. special exponential functions. So there's a bunch of exponential functions, right? Any base that you can pretty much think of. But there's two in particular that come up a lot. Two particular bases. The first one is the base 10 exponential function. And that means f of x equals 10 to the x. That's your base 10 exponential function. Makes sense? The base is 10. Why do you think base 10 comes up all the time? Or comes up frequently? Our number system is base 10, right? Isn't our number system base 10? We have, remember I said a computer is binary? Computer only knows zeros and ones? That's base 2. Two things are possible. Base 10 number system we can create all of our numbers from those 10 numbers, right? Every number that we can ever write down is based on those 10. There's no like 11th option or 12th option. Agreed? Now there are other bases, there are other number systems. There's like hex, you could do like a hex base, but we don't see those a lot, right? We don't see them in the real world. So base 10, why do you think we like base 10? What do you think inspired humans to use base 10 instead of base 8? Okay, well that's because it makes sense to us that way. I mean, if we were born and we lived in base 5, like that's what we always used, then we would look at base 5 the way we look at base 10. It's just like that's what numbers mean to us. Why do you think we decided to use base 10? 10 fingers, right? Like when we started to understand counting and stuff, right? Like if we didn't have opposable thumbs and we just had 4 digits on each hand, we would probably be in a base 8 system because that's what we would have started our counting with. Would have made more sense that way to us. But 10's what makes most sense to us because of our fingers. I have to check the accuracy of that historically, but that seems to motivate it, right? Okay. That's one base. Now, what would this graph look like? Left-hand behavior would be what? Left hand goes to 0, right hand off to infinity. Okay, now the other base is what we call base E. And this is called the natural base. The natural base. Now, earlier I had put up here pi, right? I had put pi up there and I said, all right, pi is a number, right? And it's about 3.14, but we use pi, the symbol for that number. How many of you have ever seen E as a number? Okay, not that E that we just got on your calculator. Remember at the end it said E12? Notice that this E is written in a different script than this E. This is more of like a handwriting E, where this is more of like a computer E. I don't know what you would call this difference. And this is kind of a capital E, I guess you could say. But that E is different than this E, all right? This E on your calculator says how many times you move your decimal point. This E means it represents a number. So this is the function. F of x equals e to the x. Everyone in this class should have, on their calculator, should have a key for doing that, for figuring out what e to different powers are. But before we do that, let me tell you what e is approximately. Remember we said pi was approximately 3.14, something like that? Right? Approximately. Well, e is approximately 2.718. Now, I could get into an entire hour-long discussion of what the importance of E is, where it came from, and all that. I'll just tell you this. As humans, we needed to figure out how to solve a few pretty tough problems, mathematically speaking. And we were looking for a function that behaved a certain way. We really needed this function to do a certain thing for us. It's kind of like the line didn't quite work. The parabola didn't quite work. The polynomial didn't quite work. The rational didn't work. And just any exponential function didn't work. We needed a specific one, and we looked everywhere for it, and we finally found it. And it is the function that when you let this base be e, it behaves a certain way. And since it's the only one that behaves that way, it kind of naturally occurred. It's the only one, it's unique. Then we call it the natural base. It was like given to us naturally. It's just, that's the one. All right? If you ever do any calculus, which again, not many of you are, you'll see how much this, what the meaning of that particular function is. For us, we just need to understand that it's an exponential function. What will its left-hand behavior be? Well, e is a bigger number than 1, right? So the left hand would be towards 0, right hand would be up. Which of these grows faster? 10 to the x or e to the x? Which base is bigger? 10, right? So this one will grow faster than this one. But it behaves a certain way for us, so we like it. So on your homework, one of the things that you'll be asked is just figure out what e to the square root of 2 is. This is to practice on your calculator, make sure you understand how to use your e button. So e to the square root of 2. Or what's e squared, right? So I'll leave that for you to take home and try and figure out. If you have any problems with your calculator, then you need to ask me next class. Now, I've been known before to come to a class after a lecture like today, to come to the next class, and I'm sitting here doing, let's do this and get on your calculator. And I have people that still don't have their calculators. So what I'll do is I say, we're going to do a quiz grade right now. If you have your calculator, you get 100. If you don't, you get a 0. All right? So if I look around next class and I see as many people without calculators as I do today, I'll probably do a quiz, calculator quiz. Everyone has to be able to do it. All right? Okay. And then, of course, you could, on your calculator, figure out how to do 10 squared or 10 to the 0.5 or something like that. Right? So you'll want to practice with that when you get to your homework assignment. Now, and go back in your notes, because I forgot to put something on there that I want you to add to. Remember when I said the 2 pictures, 2 possibilities? We had this one, and we had this one, right? A less than 1, greater than 0, A greater than 1. Just add one thing. This side right here is called exponential growth. This one is called exponential decay. Anybody here taken any biology or chemistry class where they talk about half-lives? You ever heard of what? Not that video game Half-Life. I say Half-Life and half the people wake up what? Half-Life? What? We're going to play Half-Life next class? That's not what I'm talking about. What is a half-life? So imagine you have some nuclear radioactive material, right? Like this. Here it is. This is radioactive. The way that radioactive material behaves is that it starts to decay. It starts to go away. Okay, so it starts off, it's almost like a fire. It's really hot. And then what happens is that after a certain amount of time, that's supposed to be half. Half of it, half of the bad stuff's gone. And then, so let's say that took 10 years. Then 10 years later, another half will be gone. And then 10 years later, another half will be gone. And then 10 years later, another half will be gone. And then another half will be gone. And then 10 years, another half. And then another half. Right? What's happening is that it keeps getting half, half, half each time. That's an exponential function where your base is 1/2. So you start off, it's decay. You start off, you had 1, right? You go out, let's say, 1 year, half of it's there. 2 years, 1/4. 3 years, 1/8. So on and so forth. Well, every different radioactive material has a different half-life, how long it takes for that to happen. It might be 10 years, or that might take 100,000 years, or that might take 2 million years. So the half-life of something, some sort of isotope or something, This is something that's calculated, and then what we do is we fit an exponential function to it, and we can say how much of it's going to be there later. Anyone ever heard of radiocarbon dating? Where they find some old fossil and they measure the amount of carbon that's in it. What they're doing is they're working backwards. They're figuring out, okay, look, how much carbon is there? Okay, if I know how much carbon is there, then I know how old it is. So they're doing like a reverse process. They're going back and... But all of that has to do with these two, exponential growth and then exponential decay. So if you hear me say decay, this is what the graph looks like. If you hear me say growth, that's what it looks like. All right, we're gonna finish 4.2. We're not gonna get to 4.3, I don't think today. Solving exponential equations. The beginning. What I mean by that is that we're going to solve some exponential equations right now, but later on we're going to do even more. For now, this is just the beginning of it. It's just the baby part of it. And then later we'll do more challenging problems. Okay, we're stepping away from the graphs for a second, okay? So please make sure you understand that. We've been graphing these things, saying, oh, this is the way they look and all this stuff. Now what we're doing is all of a sudden we're going to try and solve some equations that have exponents in them. So let me give you an example. Can you solve this for x? Tell me what x needs to be here. 3. X is 3? How did you do that? Just looked at it, right? 2 to what power is 8? 2 times 2 times 2. 3 times, right? Now, that works, but we need a method for doing this, a better method than just guessing, or not guessing, but just like an educated guess. So I want you to see how we can get to this answer a different way. What is the base over here? 2. Okay. Can you rewrite 8 as 2 to a power? Okay, 2 to what power? 3, right? So I have 2 to the x must equal 2 to the 3. Doesn't that mean that this has to be equal to this? So therefore x must be 3. That makes sense? Now you wouldn't have to do that for this problem, but I would never give you this problem. So, but the idea is this. The idea of this is what I'm going to do on the next problem. How about this? How about 16 to the x equals 4? That one as easy as this one? (16) to what power gives you 4? All right, so let's go back to this. This one, the base here was 2, right? And we rewrote the 8 as 2 cubed. This one, the base is 16. And can we rewrite 4 as 16 to the power? Well, can we rewrite 16 as a power of 4? Look at it the other way. What is 16? 4 what? Squared? Now, so is this the same problem? Am I looking at the exact same problem right now? That's 16, right? To the x is still 4. All right. Now, do you remember a property of exponents? If you have something to a power and then all of that to a power, what do you do to those two powers? So we had these properties so you don't confuse them. If you have the same base, different powers, you add the powers, keep the base. If you have something to a power, you multiply the two powers. So when I'm looking at 4 squared to the x, what am I going to do to these? Multiplying, right? So isn't that the same as 4 to the what? 4 to the 2x equals what? 4, but can I rewrite 4 as 4 to the 1? Yes? Now, just like we said before, if these are the same 4, 4 here, doesn't that mean that that has to be that? You mean, I'm saying that means 2x has to be 1 for this to work? Can you solve that for x? 1/2. Divide those sides by 2. X is 1/2. Now, do you believe that? Come back over here and look at it for a second. X to the 1/2 equals 4. Does anyone remember what it means to raise something to the 1/2? It's the same as what? Square root. Raising something to 1/2 is the same as a square root. Another property you may or may not remember. The nth root of x is x to the 1 over n. You might want to go and review exponent properties. In fact, if you want to know in your book where you can review exponent properties, I can tell you. Page 21. Let's see. See if 21's up. Yeah, 21 has all your exponent properties in it. It's a bunch of them. Page 21, section R3. Okay, how about this one? All right. How about 4 to the 3x equals 1/32? Oh, really? Would I do that to you? I think I just did. I'm sorry. Do you see the difference now between these two problems?
Mhm.
This is just, all right, man, 3, okay, big deal. This one, no one's going to be able to sit here and just look at that and tell me what the answer is. At least I don't think anyone will. So we need a method, right? What was the method we used here? We looked at the bases. We said, okay, can I get the base to be the same somehow? Well, I can't turn the 4 into 16, but I can turn the 16 into a 4, right? So looking over here, any ideas? Maybe I should guide you through this one. Just tell me whether or not this is true. Is that true? Is 1/32, 32 to the -1. Okay? Now, can you rewrite 4 as something base here, or can you rewrite 32 as base 4? Like, is 32 4 to something? What are the powers of 4? 4 to the first is 4, what's 4 squared? 16, what's 4 cubed? 64, right? So 32 is a multiple of 4, but it's not a power of 4. So 32 cannot be rewritten as a power of 4. Do you recognize 32 as something, though? I mean, it is a power of something. What is it? 32 is a power of what number? Right? Think about your megabyte thing computer, right? Isn't that a power of 2? Okay, so 32 is what is 2 to what power? 2 to the 5th? Do you all agree with that? Now over here on this side, that 4, is that a power of 2? Yes? It's 2 squared, isn't it? You mean to tell me that I can rewrite this problem like this? I could rewrite the left side as 2 squared and then to the 3x. That's the same left side. And I can rewrite the right side as, what did we say? 2 to the 5th, but then all that to the what? -1. But that would still be the same exact problem. Now, the property of exponents that we just used over here, something to a power, what do you do to the powers? Multiply. You mean to tell me that this turns into 2 to the 6x and that this one turns into what? 2 to the -5? And now don't we have the same base? Doesn't that mean that that has to be this? For these to be equal? That means that 6x must equal -5, which means that x had to be what? -5/6. So x had to be -5/6. So that's the answer over here. If you want to know what x would make this equation true, you're going to have to plug in -5/6 right here. If you do, compute that, it'll come out to be 137. No way you'd been able to just look at that and see that, though. So the moral of the story here was we looked at the problem, we tried to look at the two numbers here, we tried to rewrite them so that they had the same base at some point and get it to work out. How about this? 100 to the x plus 2 equals 1,000. Any ideas? They're both base 10, right? 100 is base 10, 1,000 is base 10. So I can rewrite this as 10 what? Squared, and then all of that to the x plus 2, right? The other side, 1,000 is 10 to what power? 3. What do I still need to do here? Multiply the exponents on this one, right? Multiply that. What's 2 times x plus 2? 2x plus 4. You have to distribute. That 2 is going to go to both of those. So you get 10 to the 2x plus 4 equals 10 to what power? Third. Now I have the same base, right? So that means that the 2x plus 4 must equal what? 3. Now that's just a linear equation. You solve that for x. Subtract 4 each side. Divide by 2. X is -1/2. Do I feel exhausted yet?
Yes.
Yeah. Then I'll ask you one last thing and I'll let you go, okay? Let's say that you were asked to sketch this. Someone came in here and said, sketch this. Let's see, what did we do? How about this? 2 to the x minus 4 plus 3. What if you were asked to just do a real quick sketch of this? What do you think that you could do with this? And could you do a little table and plug numbers in and figure out what you get out? Yeah. But remember when we had the toolbox functions? Remember when we were doing something like this? Like if we wanted to sketch x minus 4 squared plus 3, we said, all right, we know this has to look like a what? Parabola, right? It opens up because this is a 1. And then what did the minus 4 inside do? Move to the right 4, and what did the plus 3 do? Up 3, right? What we want to see with this problem is that we kind of have like a toolbox function. It's exponential, isn't it? It's an exponential function. Our x is up here, our 2 is down here. So this should look like 2 to the x. That's what it should look like. Didn't we graph that earlier? We did a t-table for that. If we take that graph that we did earlier, all we have to do is what? Move it to the, what does subtracting a 4 up there with the x do? What does subtracting the 4 with the x here do? Right 4, and then this, up 3. So what all this is the graph that you already know. You know 2 to the x looks like this. To graph that, you move the whole thing to the right 4, so just take this point, 1, 2, 3, 4, and then move it up 3, 1, 2, 3, and then you draw it again, wouldn't you? Like this? Okay, what about this horizontal asymptote that was here? What's going to happen to it? It's going to go up 3, right? It'll go up 1, 2, 3. It'll be here. So I should make that go like that. See that? In your homework, you're asked to graph a couple of these, and you do not need to make tables for these. You just need to know what it basically looks like and then move it left and right. Left, right, up, down. Okay, let me give you your homework assignment. Okay, page 432 is where it starts, and 9 through 19 odd, 25, 27, 39 through 61 odd. Oh wait, hold on. 39 through 45 odd, and then skip a few there. 53 through 61 odd. That's what I recommend you do for next class. We're ending class a little early, right? We're supposed to go till 4:40. So if you need to talk to me about your test or your grade or anything like that, please feel free to hang out.